Okay, so after the stuffed presentation on Tuesday, we'll have a bit more relaxed go today. And what I want to present to you or discuss with you is a kind of weird approximative scheme to handle quantum impurity models, and that goes under the name resolvent. Well, that's nice. Resolvent perturbation theory, well, let's write down the acronym NCA, which, depending on how you view it, is called non-crossing approximation or never correct approximation. Okay, so we've learned a little bit about quantum impurities these past few days and how to treat them. You've seen IPT. Michel has introduced you to CTQMC, and you will also learn about CTQMC and the hybridization expansion. Plus NRG, I've told you a little bit about. Maybe you didn't really get the full idea, but there seems to be lots of things around, so why another one? The answer is quite simple. First of all, it paves the way or the path for Philipp Werner's talks tomorrow, because he shows you a Monte Carlo variant that builds on precisely this type of approach, like the CT-int, which you've been using probably yesterday, is built around the expansion in U. Second, all of these methods have their values and efficiencies. For example, if the impurities become more and more complex, especially if you want to use Monte Carlo, computation times become longer and longer. The resources necessary become larger and larger. And if you've got only one of these small Macs here with 4 processors and humble 8 GB of memory, you probably long for something that can do the calculations on this machine, and you don't have to apply for computer time in Germany or wherever for large computers. And this is precisely this approach. It has deficiencies too. So we will see in the end it has a very severe deficiency. But on the other hand, for several applications, and particularly if you want to have a quick and dirty and nevertheless, at least qualitatively, decent approach towards orbital impurities, that might be a way to do it. Okay, so there are lots of, well, this is a very old technique. It goes back to the middle 70s, I think 1974. It has been introduced by Keiter and Kimball. They didn't realize at that time that it's really something worth. They just made it for fun. So I don't want to direct you to these old papers, but what you want to look at is the ubiquitous book by Alex Hewson. I don't write down the title. You've seen that several times before, so don't just remember your earlier scripts. Then there is a review, well, actually it's not a review article, but John Wilkins' group always writes extended papers. They amount almost to review articles. This is an article by Bickers and co-worker from PRB. Ooh, this blackboard is funny. From PRB 36. Page number 236 from 87. This presents a slightly different approach to the whole business, which may or may not be more convenient to understand for people having done conventional perturbation theory or diagrammatic techniques. But it contains all discussion of the algorithm, how to program it, and how to do things properly. So that's like Krish's paper on NRG. That's the standard if you want to really do the coding, which I can't do here, of course. I mean, this would take forever. And then there's, so this is actually so one band or one orbital and U going to infinity. That's the most strongly correlated business you can do. And if you want to look for an article that describes how to handle actually multi-orbital systems with finite Coulomb action, you might want to take a look at Markus Zöllfeld's article. which you can also find in FysRef B 6.1 in this case. Well, 12, 80, 10, and that's from 2000. So that's a bit of literature. Oh, one thing I would like to tell you, I have as you can see, this is not handwritten, this is a text script, so the PDF, and I will give it to Indra, who will distribute it on the net, so you can actually take the whole script, and there's everything in there. So those who are lazy writing can relax. Okay, so that's the literature. Let's start with the first part, single impurity Anderson model and resolvents. Okay, you've seen the single impurity Anderson model quite some time already, so I don't want to write it down again. It's a lengthy Hamiltonian. It takes up at least several minutes to write down everything. You remember there was this band states, which I typically called C, with a dispersion epsilon k. Then there was this localized system with an energy epsilon d, a Coulomb repulsion U, and the operators were referred to as D operators. And then there was the hybridization, V, between those band states and the localized states. Yeah. So there are three terms, the single impurity Anderson model has three terms, which I call HC plus HD plus HDC. Okay, so that's clear what's meant with these single terms. And also you remember the energy scales, or the scales in the system, was the bandwidth W. Bandwidth W of the conduction electrons. Then you had the ratio epsilon D over W, U over W, if you like. And finally, it turns out that the hybridization V itself is not that important. It was rather the combination, let's call that gamma 0 over W, where the gamma 0 is given by, well, in the most general case, pi over number of sides, sum over all states k. Then you have a Vk modulo squared, delta of, okay, delta of omega minus epsilon k. Okay, this can generally be frequency dependent, and you know that this frequency dependency is absolutely important for doing DMFT, because there this self-consistent generation of the bath or the hybridization function precisely will give you an energy dependence you don't know in advance. That's the big problem there. And here I just put in gamma 0 of 0, which means that you take the value of this hybridization function, take this value of the hybridization function at the Fermi energy, and I will also call gamma of 0 simply gamma 0 of. Yeah. Okay, these are the objects, the energy scales in the system, and you also know already by now that there will be a dynamically generated energy scale called the Kondo temperature, which appears due to the many body effects in the system. And one of the important issues, there are two important issues. First of all, a perturbation theory that should be feasible to treat correlation effects in the way we want them to handle is it should be able to generate such an energy scale. It should be able to generate an exponentially small energy scale. That's also quite important. Otherwise, you will go awfully wrong with all correlation effects. And finally, you also should see Hubbard bands. I mean, this is the second part. These big wicks out there, they should also be present in the theory, because otherwise you don't get the charge fluctuation physics right. Good. Now let's see whether we can get to this part. Okay, what you've learned up to now is you have seen the IPT, which is nothing but the second order PT in U. And this was restricted basically to small u. It works astonishingly well, even at least qualitatively, if you make u larger. You in fact get Hubbard bands, which is quite amazing. One warning, never try to do this thing self-consistently. As soon as you try to make a skeleton expansion out of the IPT, that is feed back the self-energy into the equations, you can do that. That would then be a correspondingly conserving approximation with all nice properties. But you lose immediately all the Kondo feature, the Hubbard feature, it becomes a vegetable. Now that's a warning. Never try to do that, make this self-consistent. Okay. So that's one approach. Now you might wonder what we're interested in, or often interested in, is the Kondo limit. And you may remember that this was given by epsilon d over gamma naught and epsilon d plus u. Oops. Epsilon d plus u over gamma naught much bigger than 1. Now, this was when the singly occupied state, or better say the charge, the electronic states are well separated from the Fermi energy and from each other. And then you're basically in the local moment regime. That was the Anderson construction. And you expect Kondo effect and all kind of funny correlation effects taking place. So that's the regime we're in. Now that tells us that we definitely have to deal with u over pi gamma is much bigger than 1, and not u over pi gamma much less than 1. So what's the meaning of pt in u in that case? Yeah. Well, okay. If it's actually not the u that is a small number, but the gamma that is a small number, let's try a perturbation theory in gamma. It's an attempt. That is, we would say that our H0 from a perturbation theory is Hc plus Hd, and our perturbation Hp is Hdc. Okay? That's just a way of defining H naught. In the other case, H naught was band states plus the F level, and the perturbation was the U. So this was the interaction term. Now we just take another one. This immediately leads to a funny, not funny, unfortunately, to a kind of unpleasant consequence, because HD is not no, it's not quadratic. It's not quadratic in D and D dagger. Yeah. In fact, it's quartic because you have the interaction term. The U term contains 4 operators, so it's quartic, and that has as one of the consequences. And you've heard about this theorem already. You don't have a Wick's theorem for the D's. Now that at first may not tell you anything because you may have heard of Wick's theorem before or might not. The importance is that all kinds of perturbation theories, the whole whole Feynman diagrammatic perturbation theory rests on Wick's theorem. It has as a consequence the so-called link cluster theorem, which means you don't have to care for the partition function. It cancels out exactly. It leads to this factorization of diagrams from high-order products of D operators into products of Green's function, and so on and so on. So that's all in this simple Wick's theorem, and we've lost it. That means there's no way we get rid of the partition function. We won't have a fine diagrammatic theory in terms of Feynman diagrams. But one can try to go on. I mean, there have been perturbation theories before Feynman, and they rested on, or before using Wick's theorem, basically, and they didn't rest on Wick's theorem, as I just said, and did work. They weren't followed further because they became quite cumbersome, but it's still possible. And that's one of the perturbation theories we're trying to develop here. On the other hand, this Hc, the conduction electrons, they are nicely quadratic in the band electron operators. So for products of C operators, you have Wick's theorem. And that means if you when you try to set up a perturbation theory here, what you will end up is a kind of mixed Feynman and how they call it, Goldstone perturbation theory. Okay, so let's try to do that and see how far we get. In Germany, when I give my lectures, there's somebody wiping the board for me, so I can continue. Usually the chairman. Chairman's too tight. Shall I tell why? Okay, you're not supposed to switch off. Yeah, that's a nice gadget, but first of all, it becomes heavy after a while. But so that limits the time for the lecture in a natural way. Okay, so again, we don't have Wick's theorem, so we can decompose products of D operators into products of Green's functions, but we have to see whether we can get something else. Good. So step one. Diagonalize our HD. Right? That's the first step to do. In that case, you end up with eigenstates. Let's call them M. And HD acting on M is EM times M. Well, that's our beloved Schrödinger equation. And since HD is atomic Hamiltonian, you can, is a relatively small finite system, you can actually do that. Now, here already comes in one of the limitations of that approach. As Andy Millis told you yesterday, there's this thing called exponential wall. And of course, if your number of states of your atom become too large, the degrees of freedom, you will hit this exponential wall. So for a D system, the wall means 1024. That's not really a problem. You can do that. You will find that later on doing this perturbation theory, the number of diagrams generated is tremendously big, but still it can be handled. And I mean, we did this 15 years ago, and 15 years ago, a gigabyte was already something way out of reach, and the processor speed was, well, probably your coffee machine today. So you could do it. So nowadays, you could probably easily do the F shell with 7 orbitals on the NCA. Maybe not on that machine, but on the decent machines you have in your lab. Okay, but then there's you hit the wall at some point. So if you want to do, say, G states or whatever, it might become problematic. But what material has G states? Okay. Now, once we have these eigenstates, we can actually rewrite our Hamiltonian in the following way. First of all, HD becomes pretty simple. It is just the sum over all of these M's, EM. And now I use a formulation with projection operators. I hope you're familiar with this dyadic representation, M. Now that's the projection operator onto the state M. It's just writing the Hamiltonian in its eigenbasis. And of course, you can also express now the coupling in these states. It has a 1 over square root of n for normalization as a prefactor. Then you have the sum over k and sigma. You now have a sum over m and m prime. And then you have a matrix element F sigma m prime. You have the Vk sitting around. You have the Ck sigma dagger. Oof. And then now comes not a projector, but a transfer operator, m prime m, oops, plus the Hermitian conjugate of that. So that object here starts from a state m and gives you a state m prime. And whether this is, which of these combinations are non-zero is actually encoded in those matrix elements. Standard quantum mechanics, what I'm doing here. I'm just saying, okay, I take a different basis and rewrite my operators in this basis. That's all I'm doing. And of course, you can also write down these matrix elements, F sigma, M, M prime. They are given by M. Now, usually, one would have here, say, a dm sigma M prime. I put in the orbital index here to show you how that whole thing will eventually work if you have a multi-orbital system. At present, to keep things simple and also to avoid having too many indices, which become at some point unreadable, I skipped the M here, but always keep in mind the whole scheme goes through for any multi-orbital system. You don't even have to use this, the combination M, you don't even have to use the combination sigma and M. You could also easily work already from the beginning in, say, a spin-orbit coupled total angular momentum basis. So that's up to you. In that case, the formulas look very much the same, except that the meaning of these indices have changed, right? So that's a quite general technique. I'm just working it out for the simplest case to keep the notation simple. Okay, so without orbitals and spin only, well, if you also ignore the spin, then things becomes a pretty boring thing. You can solve that yourself, by the way. Try to set everything spin degeneracy off, switch off orbital degeneracy, and see how the model looks, and try to solve it. It's straightforward. Exercise for bad weather days, which I don't know whether this happens here. Okay, so in that case, the states M, I think Antoine has written them down already. The states M amount to 4. Namely, you have the unoccupied state. There is no electron in your atom. You have the singly occupied state, which I typically, and Antoine also called sigma. So that means one electron with either spin up or spin down in your state. You have the W-occupied state. Okay, and now one has to show, well, have to become explicit, because now, because we have to deal with fermions, now it makes a difference how you define that state. And I define it that way. Yeah? So the down spin stands to the right, then comes the up spin. That means if you act an annihilation operator on that object, and you want to delete the down spin, you have to commute it once with a upspin creation operator that gives you a minus sign. Okay, always. I mean, these fermions, they are sometimes a bit beastie. One has to be careful about signs with them. And the energies belonging to that are 0. Well, if there's nothing, then that can have an energy. They are epsilon d. That's the singly occupied state. As long as we don't have magnetic field, they're the same. And finally, this is 2 epsilon d plus u. I mean, this is what Antoine already told you on Monday morning. And finally, you can work out the matrix elements, F sigma M. Okay, F sigma 0, so F sigma 0. Sigma 0 means now, so this is the spin and this is the state sigma, so please careful. Well, this is simply 1. Well, I mean, so the M prime is 0. No, okay, now I mixed up my own notation. So the M prime is sigma. You delete, delete, annihilate a sigma electron. That gives you the empty state, and the overlap of the empty state with the empty state is 1. And the second matrix element is F. I have to be careful now again with the notation. F sigma, then comes minus sigma and 2, which means now you have the M prime here. That is the doubly occupied state. Remember, this was up, down, right? Then you delete or annihilate one of these creatures. If it's up, nothing happens. If it's down, you get a minus sign. And this means that it is sigma. Yeah? So it's 1 if those two are equal. It's minus 1 if they're different. Wrong. It's plus 1 if they're up, and it's minus 1 if this is down. Okay, so this is the basics. Now we have generated our Hamiltonian. We know the states, and now the question is how to proceed from here. Okay. So you get a moment rest, and I have to clean the board. As I told you in the beginning, we do have to actually care for the partition function, because in contrast to the standard Feynman perturbation theory, where due to the linked cluster theorem, the partition function cancels out of all perturbation series, this is not the case here. So if we have to calculate it, we better start by doing so. Remember, partition function of the system is given trace e to the minus beta h, where beta is the inverse temperature. And the question is, how can one do the calculation here? Now let's use a kind of subtle observation. And I don't want to write that down. And I asked the mathematical physicist to watch the nice nature outside for a moment. Namely, since we're dealing with a solid, the solid is finite. You've never seen infinitely large crystal. So it's always confined in a finite volume, maybe very large compared to the atomic distances, but it's finite. Now, any finite quantum mechanical system has always a discrete set of states. Okay? The reason I'm using that is the following, because I want to write that in the following funny way, namely as an integral circulating all singularities of some object. Let me write down the formula, and you will see immediately what I mean. Right? So if you have a discrete spectrum, if your Hamilton operator has a discrete spectrum, this is an absolutely well-defined object, because the residue theorem tells you pick the eigenvalues, put them into the e to the minus beta z, the 2 pi goes away, and what's left is the trace over the eigenstates. Fine. So that's just a fancy way of rewriting, but you have to make the assumption that you have don't have a continuum of states. Otherwise, you're into trouble. And that's also a kind of question how to perform limits in the end, because you have to be careful in which way you perform the limits going to the thermodynamic limit and to t equals 0. But I want to discuss that here. Encircle all I. So okay. So two things. First of all, you need a discrete spectrum. It has to have finite support, but that's usually the case. It might be large, but it's finite, and it has a lower bound. Again, I mean, you have to stop and interrupt me and ask questions if there's something not clear. I mean, these are up to now rather simple mathematical manipulations. There are subtleties in there, but if you're fine with the physicist's point of view, nature will do everything for us to get the right answer, then we can continue here. Okay, now I rewrite this in another way, namely I perform a partial trace over the band states. Yeah, I write it in the following way. I say this is equal to the partition function of the band states. Now this I call C, Z, C, subindex and superindex 0, which means this is the partition function of the band states only, non-interacting, no impurity, nothing. Then I have the integral 2 pi I e to the minus beta z. Now let's write the trace over the d states, the sum over m. Then I have a second 1 over z z0. That's the band electron. And then I take the trace over z. I have here an m. I have here a c. I have the 1 over z minus h, a c, and an m. Okay. In fact, I could have written this one here. I could have written this as trace over d. So that's a partial trace over d, and this is the partial trace over c. I just written it out completely. And now these c's are the eigenstate of the band Hamiltonian. Okay, I'm sorry. Can you read this, by the way? I think this is I have to be careful. Okay, let's write it down again. So hc times c is ec. Simply this eigenstates and eigenenergies of the band electron system. Now what I do in the following is I simply shift this integral here by ec. That is, my partition function becomes the band electron partition function. We have the integral over dz 2 pi I on some curve e to the minus beta z. That doesn't change. Then we have the partial trace over the d states of the following object, 1 over z c0. Now I have to write into the next sum over all band states. Now comes the e to the minus beta ec. Right? I shifted the integration from z to z minus ec. Simple shift of integration. I can do that. Then I pick up this additional Boltzmann factor here, and what's left is c 1 over z minus h plus ec z. And the trace. So this contains both c and d states. I have the partial trace of c states. So that object is still an operator in the d subspace, and I take the trace over the d states there. Now this object here, this whole thing, we call R of z. And this R of z is the so-called ionic resolvent. Yeah, you see this is actually, those who know these terms, this is the resolvent operator of the Hamiltonian, 1 over z by h. It tells you about the structure of the spectrum. And like that, it's a partial trace of the, or actually partial average over the band states, because now we have here the terminal average over the band states. So it's a terminal average of the band states in a particular way. And this then is kind of telling you something about the spectral properties of the impurity. And in that sense, it is called ionic resolvent operator or ionic resolvent. Or simply ionic resolvent, or ionic propagator. Nothing has happened very much up to now. I mean, I've rewritten things in a very funny way. We will see in a moment how that helps us, or whether that helps us at all. Yes, sure.
It could also be the M sandwiching those guys, right? So that's a complete set of states. So that's MC.
That's in the trace here.
Oh, that's your thing.
I tried to put this on the on one board, but it doesn't work out. So that's contained in the trace. Now, this allows us now to define a partial partition function zd, which is simply given as the integral over our contour dz over 2 pi I e to the minus beta z. sum over m, and that's what Jay just said, m r of z m. That's now the way you can represent the partition function of the impurity, of the atom. This is, so to speak, in the sense of the modern language of entanglement and these kind of things, this is a reduced density matrix, nothing else. It's just a very funny way of calculating a reduced density matrix. That is, you'd have the bath, that is your band electrons, you have the system, that is your atom, and you take the partial trace over the bath, and that leaves you with a reduced density matrix of the system. That's basically it. Just a funny way of writing things. Now, there's one thing we know, because the structure here tells us 1 over z minus h. H is a Hermitian operator, so it has only real eigenvalues, right? And that tells us that r of z is actually analytical everywhere except, well, if it was analytical everywhere, it would be a constant, if you remember your math courses, except on the real axis. This is crazy. Okay? But that means, you won't wipe the board for me. No? You don't want to wipe the board for me. But that means, actually, that you can do the following trick. Now, let's assume this is our complex plane. This is the real axis. This is the imaginary axis. And our contour somehow is that. Oops. Right, that is our C. And anybody knows which direction I have to go through it? Okay, now what we know is that, okay, here we are. We know that all singularities of our resolvent are actually located on the real axis. So what you do typically is then to say, fine, I don't want to do the contour, but since nothing happens here, I can also replace that by one branch living slightly above the real axis and one branch living slightly below the real axis, assuming that nothing happens out there. Well, this is guaranteed by two things. The first thing is, as I mentioned, the Hamilton operator is bounded from below. So at some point there will be nothing out here. And the second thing is that, well, in the large, for positive, large positive real energy, this object will kill you, or will kill the integrand. So the infinity is taken care of, and then we can deform our contour so that we now have this thing, and that can be transformed into an integral from minus infinity to infinity, now over omega, e to the minus beta omega, sum over m, rho m of omega, where does anybody know what rho m of omega has to be by that construction? Well, excuse me? No? Well, yeah, you know, I know, yes. So what you do is you take this guy slightly above the real axis, you take that guy slightly below the real axis, walk that way, walk that way back. So the one above the real axis comes with a minus sign, the one below the real axis with a plus sign. That gives you something at plus I delta minus something at minus I delta, which is the complex conjugate. So it gives you imaginary part, twice the imaginary part. This cancels the 2I here. The 1 over pi is left, and that's why you have the rho m of omega is minus 1 over pi times the imaginary part of this r n at omega plus I delta. Okay? That's the spectral function. So that's the spectral function of the resolvent. Okay. Again, this is up to now absolutely exact. Well, except for maybe that slight subtlety about writing a trace as a contour integral. It's absolutely exact, and it doesn't help us really in doing calculations, up to now at least. But as I will show you in a moment, it's a starting point for a perturbation series. Before we do that, I would like to give you an idea. Before we do that, I would like to, could you pull down the screen and switch on the projector. You may want to take a look at Kinkakuji, which is a wonderful temple in Kyoto, while I write down some boring formulas. Okay, let's try to understand what these ionic propagators will do and why they will do it. And that will also set the stage for later calculation. So first of all, let's put V equal to 0. What does that mean? Well, in that case, there is no coupling between the D and the band states, basically. So everything that happens is that the 1 over Z minus H plus EC times the vector C will cancel the EC in the denominator. In that case, the resolvent operator is simply 1 over Z minus HD. As simple as that. And that means that the rho m of omega will be a delta of omega minus EM. Well, it's not really so fascinating because that's what you would expect if you have a Hamiltonian, you calculate its spectrum, you calculate the resolvent, the spectrum is discrete, you will get poles at the eigenvalues. Okay, let's try to plot that nevertheless. That's shown here. On the left-hand side, A, so we have three eigenvalues of a Hamiltonian at E0, E sigma, which I think is the ground state in most cases. You have a second one which sits at 0, that's the unoccupied state, and depending on the value of u, that is the W-occupied state, it can sit anywhere in between. So that's the situation you start from. Yeah? And now what happens if we switch on, when we switch on our hybridization? And that's now qualitative. Yeah? We will, actually, the right-hand side is the result of a calculation based on the perturbation theory I will discuss with you. But it shows the general features you have to expect. Now, let's consider one thing. The ZD is the partition function of the atom. The reduced partition function of the atom, if you like. So it better exists, right? Which means that you have the following relation that the free energy of the electrons is minus kB T times this log ZD. And this you want to have finite, right? It should be bounded from below, namely by the ground state energy. Now, if you remember this formula, ZD is given by minus infinity to infinity, d omega, e to the minus beta omega, summa over m, rho m of omega. In order for that integral to converge, the rho m's have to decay exponentially, like e to the beta omega, for omega going to minus infinity. Otherwise, boom. Which means that in this region, there must be an exponential decay. And that's what you see here. Now, at t equals 0, if you go to t equals 0, this represents the ground state or the internal energy. In a discrete system at t equals 0, this is something related to the ground state energy. You also want to have that to be finite, which means that at t equals 0, because exponential decay at t equals 0 means boof, step function, that there has to be a cutoff here at t equals 0. And this cutoff is common to all the propagators. They can be 0 before that, but they have to be 0 at least when they hit this cutoff. There's a threshold energy, and that's the ground state energy. Right? And what they do in the vicinity of that ground state energy, that depends on the system. So what I've shown you here is basically a result of this calculation. You see again the empty state, which is situated around 0 with a certain width. Well, you have charge fluctuations now, that's fine. You have the W occupied state sitting around E2, a little bit shifted, but that's what you expect from perturbation, from interactions to do. They shift things a little bit around, but otherwise they broaden it. And then there is this very big creature. Well, this was the singly occupied state, formally. It has now shifted down here, and that's the shift of the ground state energy. That's the energy gain through the hybridization, and the new ground state energy is sitting somewhere here. Now, if you look very carefully, you also see that there's a black line lurking out here. And that black line tells you, well, this guy here, although it has its maximum weight around here, has become a sizable influence at the ground state. Likewise, the W occupied state, well, it's not that big, but it's still there. And if you make the analysis a bit more carefully, you will actually see that it is this one, the peak here, which sits a little bit below the peak here. So that means the ground state is actually dominated by the empty state, not by the singular occupied state. But the empty state is a singlet. So that tells you the ground state is dominated by a singlet here, not by the spin up, spin down, by the doublet, Kondo. That's the manifestation of Kondo in this type of representation. Very subtle, yeah? But that's how you see it. And that's what we try to calculate, and that's actually, as I just told you, that's what the perturbation theory I will discuss now with you gives you. So the physics is there, and you can really understand what it means. And in fact, what you can do is if you really try to estimate the difference, I mean, there's a divergence, not really a divergence, but there's a maximum here. And the difference between the maximum of that one and the maximum of that one, that's a Kondo temperature. Okay, fine. So is there a no-show? Mute? Blank. Blank. Good. And I guess if I push the up, modern technique.
So Thomas, this
yes.
lower cutoff,
Yeah.
that can be also seen as you said that the band states have a lower bound.
Yeah.
So when I hybridize, I cannot go below the energy.
Yeah, but actually the lower cutoff, I mean, that depends a little bit it depends on the impurity. You can actually push the D level below the band cutoff. And then the thing would still look like that. So you still have a very sharp, but still resonance. And this resonance actually, that transforms into something at the Fermi energy in the spectral function. That's quite important. So the arguments actually stay. Can I switch on the lights again? Okay, so that's what you expect. That's what you see from the calculations. Now let's go to the next step. Oops. That's the resolvent perturbation theory and the non-crossing approximation. In fact, there was a discussion on those who attended Philip's talk on Saturday, I think it was, on the non-equilibrium. He actually used this NCA type of approach for doing non-equilibrium calculations. That's also a nice thing. You can extend it to time dependence calculations. And there we talked about NCA, OCA, ECA, BLACA, and whatever. There are different flavors. So there are extensions which work in one way better, but they become numerically more and more complicated. So what I present you here is the simplest version, which is easy to code, which is rather stable, has little numerical problems, and actually is good for getting a qualitative account of physics in the strong correlated regime of multi-orbital systems. Okay. Okay, the H0 I've defined you before. H0 was Hc plus Hd. And now let's write the resolvent. I mean, maybe you have seen that already. If not, it's a nice way of fiddling around with things and writing in funny ways. Let's write this in the following way. So this is the resolvent we have in our ionic operator. Still written there somewhere. Yeah. And that we write H naught plus EC. So H naught was, again, simply Hc plus Hd plus, and then comes the second term, which we write as 1 over Z minus H naught plus EC, HdC 1 over Z minus H plus EC. Oh, actually, I should have given you a reference. I can do that later on, put it into the script. There's a wonderful reference by two guys, Keiter and Morandi, from, I think, the early 80s, which make a very mathematical treatment of that. And it's nice to read. So those who love mathematical physics will enjoy it. The others will probably get scared. I was exposed to that as a diploma student. This was the first article my supervisor gave me to read this. Well, I stick to it. But it's, I mean, this is something that tells you what you actually can do with mathematics if you like to. Okay, so that's the way of writing it. You may want to show as an exercise, so that's a very simple exercise, that this is indeed true, just by manipulating things. Of course, this can be repeated. I don't want to write this down because it becomes lengthy and lengthy. You see the point. Here you have the same again as here. So you just insert that again, then you get a second order, then you insert it again, you get a third, and so on. So you get a series, actually. If you do that iteratively, you eventually will end up with a series in HDC, power series in HDC. That's what we want to have. Not quite, it's something, yeah, but it's on an operator level, so one has to be careful there. Yeah. Okay, now something we have to take into account. We want to perform a trace over the band states eventually. Yeah, that's in, oops, the formula is gone. That's what we want. That's what we do with the C here. We multiply it with C from the left and the right, and take a trace over the band states. But that tells us that if I do that, starting from some C on the left and some C on the right, I better end up with the same state. Otherwise, it's 0. And that tells us also that if I have this perturbation series, I need to have an even number of HDCs, because HDC changes the number of band electrons once. In order to get back, or to be able to get back to the same number of band electrons, I have to have that at least twice. Yeah? A very simple argument. So the perturbation theory is, once inserted into this trace expression, actually survives only even numbers. There's another thing which is true for our particularly simple problem. Okay. ... Again, it's written in the script, so if you're patient and wait for a few hours, I guess it will be available on the net, and you can read everything I've been telling you up to now in detail. Okay, so a particular simplification here is that actually, if you calculate the matrix elements of our resolvent operator with respect to the ionic states, is diagonal. That's true for that particular simple system. it must not be true in general, especially if you have a multi-orbital system where you in particular may have actually couplings through the hybridization of different states, then this is not true anymore. This is something actually which can be treated within this approach quite easily, but which kills immediately every Monte Carlo you want to try, because that leads to a sign problem that is as bad as it can be, right? So in case you have off-diagonal hybridization matrix elements, this is one technique that still works with all its deficiencies, but Monte Carlo might be dead already. And actually, it is not unimportant. There's one particular example which we studied long, long ago. That's lanthanum manganate. Particularly if you want to study the true low-temperature ordered phases, like G-type orbital ordering and an A-type antiferromagnetic ordering. It turns out you have to actually use the D states not according to the normal LM, L equals 3, M minus 101 description, but you have to take certain linear combinations that accommodate eventually the Jahn-Teller distortion of the lattice. That happens at some point, and it changes the symmetry a little bit from cubic to orthorhombic, I think. And then you get a slightly different combination of d orbitals that do the job. And if you do that, that generates, in fact, if you then look at the LDA Hamiltonian, that basis, that generates off-diagonal hopping matrix elements, and that gives you this type here. But it can be done. So just to mention that this is not quite out of the world, but it can happen. In most cases, if you just have simple cubic materials, that won't be the case, but as soon as you have, say, orthorhombic or tetragonal distortions, tiltings of your octahedrous and these kind of nasty things, then in principle one should be careful and look whether this is necessary. Okay, now the best thing you can ever do when you devise these type of approximations or perturbation series, do one term explicitly, so you see how things work out. And let's do that for the example, second order for our R0. That's the unoccupied state. So the R0 in the second order as function of Z is, the zeroth order contribution is very simple. That's just 1 over Z, right? I don't want to write this down here. So that's the, if you want to say it's the second order correction. And according to what we just said, that is the bare band conduction electron partition function. Then you have the sum over all band states. You have a C here. Now let me make use of the fact that the C's are the eigenstates of the band electrons, which means I can also take the e to the minus beta EC into the expectation value as e to the minus beta HC. Then you have a 1 over Z minus HC minus EC. That's this one here, okay? Because HD is 0. So we have the 0 state here. Next step is we have the 0 here. I pulled this through already, but I can't pull it through very far because at some point I hit my HDC, which prevents me from moving it on further to the right. Then I have the second part here, namely this guy, lurking around. 1 over Z minus H0 plus EC. Then there comes the second HDC. And now from the right, I have another 0, which I can pull through until I hit this one here. And then you have another 1 over Z minus HC, because the HD has been eaten up by this 0 here, plus EC and a C. Okay, this is the second order contribution to the unoccupied resolvent. lengthy. Well, that's okay. Okay, now let us think a little bit what things look like. And yeah, okay, so zero acting on HDC is equal to 1 over square root of n, sum over k, and sigma. And now you have to remember the way this hybridization was written with these projection or transfer operators. And it turns out that the story you get is Vk. Then you have a Ck sigma, actually dagger, right? Because you have to go to the left here. And then you end up with the state sigma. Now, that's what HD does. It creates the state sigma. It actually annihilates, looks a bit funny, annihilates a bent electron because you have to act it on the on the bra, sorry, and then you get this type of hybridization matrix element. And the opposite is true if you act HDC on 0. You may want to write down the formula yourself. It's the same, just the transpose of it. Okay. Another thing, and that's something you either have seen already several times in your physics life in theory lectures, or you may want to show yourself. It's a kind of nice. It's a kind of nice exercise in using those commutation relations of fermionic operators. Namely, if you do that one, you can actually commute that through. So you can put it on the other side. At the expense that you have to commute this guy here. Now every commutation of the H naught was sum over k, epsilon k, Ck sigma dagger, Ck sigma. And Ck sigma dagger, Ck commuted with the Ck sigma gives you again the Ck sigma times an epsilon k. And then you collect everything up because that happens, you expand this in a series, do this term by term, resum the series, and what happens is that you get a z plus epsilon k minus H naught plus EC. Right? So the commutation just gives you an EC in the denominator here, and you can do the same thing with minus H naught plus EC, Ck sigma dagger, which gives you a Ck sigma dagger, and then not enough space, minus epsilon k, that's the difference here, minus H naught plus EC. Again, this is a nice exercise to play around with these commutation relations, and I'm pretty sure you must have seen that in several other connections. For example, to calculate the Fermi function, that's one way to do it. In that case, you use the e to the minus beta h and pull through the c from left to the right, and then you get the e to the minus beta epsilon lurking out. Okay. Well, we're putting everything together. This means our contribution of second order to our resolvent, R0, is 1 over z. Then you get a 1 over n. That comes from this 1 over square root n squared here. Then you have a sum over k, a sum over k prime. This comes from the band states. You have one sigma sum. You have a vk. You have vk prime. You have 1 over band electron partition function. You have a sum over all band states. You have a matrix element C, e to the minus beta EC. Then you have a C dagger K sigma, C K prime sigma, C. You see that's lengthy. And what's left is 1 over Z minus, okay. because that object here, that object creates a sigma. Well, if you pull that if you now pull that through, right? So the sigma ends up on the right-hand side, and then you see the sigma acting on the H naught gives you a E sigma. So that is times 1 over z. Now there was a plus epsilon k coming from one of these commutators here. So there's a plus epsilon k prime minus, well, and now it's just E sigma. And of course, you still have the EC sitting down here, but the C acting on, where is it? The C acting on that one will eventually erase that. So the EC has vanished. It's just the combination epsilon k prime. I'm sorry, this is hard to read. Epsilon k prime minus E sigma. And then from all these things, there's the last term, and this was z minus hc plus ec times c. Now hc times c gives ec, so that goes away, and there's a simple 1 over z left. So that's the long story, a little bit shorter. Now, this one here, you should recognize. That is simply the expectation value of the number operator for the band electrons. Those are quadratic Hamiltonian. So this guy is simply delta k, k prime. And this is then the expectation value of the number operator, which is nothing but the Fermi function. And this f is the Fermi function. And that means that after some short break, so we could put on advertisement right now. Might be a good idea. That means that the final contribution to the second order empty state propagator can be written as 1 over z. That's the first one. Then let me put this into parentheses. N sum over k and sigma. Now delta kk prime gives you a vk squared. F of epsilon k comes from the band electrons. And then divide by z minus plus epsilon k minus E sigma times 1 over z. Now this looks really nicely compact, right? Much better than before. And so the next step you can actually see is, well, this here very much looks like, this combination very much looks like the hybridization function you know already. And in fact, you can write this in the following way. You can perform the K summation by introducing a delta function, then collecting this delta function together with vk squared and so on into an integral the epsilon over pi. And now here enters our beloved hybridization function, gamma of epsilon, f of epsilon divided by z plus epsilon minus E sigma 1 over z. And you see, this is something you, in principle, can possibly actually calculate. Now, if you assume a constant gamma here, which is a typical, I think somebody called a Wilson thing yesterday. If you introduce a constant gamma here, this gives you logarithms. There they are again, the logarithms. And in fact, you need them here in order to form these shifts and singularities at the threshold. Okay, good. So this was the second order. And now you know how to proceed. Well, if you're in this business, you immediately know how to proceed, because the structure we've just seen survives to all orders. Yeah? it becomes lengthy. The blackboard wouldn't be sufficiently long enough to write down the fourth order in full beauty, but eventually it will contain the same elements as here, namely it will contain a series of HDs. The series of HDs will generate a series of ionic states. The band electron operators, you can, using these formulas, pull through to one side. It's up to you which side you want. And so eventually what you end up with is a series of operations of the sort M, D, sigma, or maybe dagger, M prime times M prime, D, sigma prime, maybe dagger, M double prime, and so on. That's one thing. And the next thing is you end up with a 1 over ZZ0, sum over all C, e to the minus beta EC, C, CK, dagger, maybe, CK, dagger, maybe, CK, dagger, maybe, and so on, C. Now this is a very, sloppy way of writing things. It just tells you you have a collection of operators. Some of them will have daggers, others won't have. Of course, in order to that to be finite, there have to be as many daggers as non-daggers, right? Otherwise, there's zero. But that's a minor technical detail. The important thing now is that this object here, or this band electron states, they can, for them you can use Wick's theorem. So it doesn't matter how many you have here. This whole thing will collapse down to a product of Fermi functions, nothing else. Yeah? So this can be evaluated as a product of Fermi functions. This one looks beastly, but it's either 0 or 1, depending whether you have the right combination here. Maybe there's another matrix element coming in. This is F sigma, basically. But you can also evaluate that. That is, you have all ingredients together now, and all you get are a series of those denominators here, with sums and differences of band electron energies and sums and difference of these objects here. That's the result you get. And it's most easily, now you can actually make use of what we've learned from Feynman and others. It's most easy to be done by diagrams. What you can do is you can replace, for example, the non-interacting object here by some wavy line. And now, better take a look at the script later on. The sigma non-interacting, you can replace by a dashed line with an arrow. And the doubly occupied unperturbed resolvent you can replace by, okay. Why did I choose that one here? Okay, that should be actually a wavy line. And that should be a wiggly line. And you can imagine that when I start to draw things now, these become indistinguishable. It's a kind of Fermionic. Then you need also the band electrons, and those you represent by the Fermi function, by a straight line showing into the left with spin k sigma. And then you have f of minus epsilon k, which is the opposite, showing to the right, and k sigma. And so these ingredients. And last but not least, you do need vertices. And the vertices are the following. Occupied, so a wavy line, going over into something that is occupied. And that has to eat up a band electron. That's the one vertex. And then a sigma goes on here. The second one is you start out with occupied state, spill out one band electron, and end up with a wavy line. And there are two more for the doubly occupied state. But in that case, you have to be careful because they acquire possibly matrix elements and signs due to the fermionic ordering. But these are the elements you need. And that's also true for multi-orbital. In that case, there are some orbital indices involved, but that's this is the toolbox for generating diagrams. So what one does now is one basically draws a horizontal line. One draws 1, 2, 3, say 4 dots on that line. Then one has to assign initial states here. Let's start out with this one, go over into that one. I mean, there's simple rules. You can't actually, by one process, jump to W occupied. This always needs 2 processes. And then, for example, let's do that one. Let's come back to that one. And eventually, you have to find at the outermost part, you have to come back to the initial state because you take traces, right? So the state you start with has to be the state you end with. And then you have to wonder how you can actually draw the lines. Well, here something has to come in. Here something has to go out. Here something has to go out. No, here has something to go in. And here something has to go out. So how can I connect those things? Well, there's only one possibility here. There are more than in other cases, but that's the way. And that's the diagram. And now you start collecting. Energies, which means you start out with a 0 here. You gather one EZ here, but since you have to collect a band electron line, that adds up 1 EK here. You collect the second one that adds up an EK here and leaves you with an E double W occupied energy down here. You spill out 1 electron, namely the EK here, leaving you the EK prime in here, which is then spilled out again here. So I don't want to write down the analytic expression, but that's very simple to construct now. Once you've done this, it's very easy. And in this diagrammatic language, our delta 2, 0 of z, sorry, other way around. This one simply looks like this one. So this was the diagram for that expression I've written down here. You see, it's fairly simple. It's just the evaluation that takes a little bit more thought. Okay, now what you can actually do is you can write down, and I will do this now in a very rough sketch. You can construct diagrams of that form, right? You can construct diagrams of that form. And of course, you have these crossing diagrams here. Now these, as a standard theory, you would call reducible, because you can cut them into pieces at that point. In fact, they turn out to be products of the same expression. And this one you can call self-energy insertions, just like a standard perturbation theory. What you can then do is, again, Dyson equation, as already mentioned. You can then write down a Dyson equation for those ionic propagators, define a self-energy, and in fact, what it amounts to is eventually that the whole series of whole perturbation series can be recast into a well-known standard form, namely the form that Rm 0 of z is renormalized into Rm of z is equal to 1 over z minus Em minus some self-energy sigma m of z. And the self-energy can be constructed diagrammatically in the normal way by just amputating outer legs here. So all you do is you have to take the things I put into parentheses, that's a self-energy diagram, and calculate them all, sum them up. And the simplest order we have already seen. which is the second order self-energy diagram, say for the empty state as function of z. Well, this is the one, and now I have to draw double lines because you have to do this in a skeleton manner, meaning instead of using the bare propagators, you have to resum all self-energy insertions, which gives you the dressed propagators, which I typically note by some double line. So that's the diagram for the second order self-energy in this perturbation theory. And you can easily convince yourself that there's a second one, there's a similar one for the doubly occupied propagator, which is, okay, now I have to draw a double wiggly line, and that is now my punishment for choosing these unpleasant type of diagrams. Right, so this now is a doubly occupied state, which means, no, I'm sorry, wrong. This comes next, I'm sorry. This is again, you want to do this for the doubly occupied state, which means the doubly occupied state is connected to the singly occupied state only, but now here the thing went into that direction, while here it goes into that direction. Yeah? So there's a second band electron line propagating together with the doubly occupied state. Yeah? Oh, this is, you have to do skeletons now. I mean, what I'm doing here is I resum the perturbation series. I call this stuff here self-energy insertions, right? And I just sum them all up into a renormalized propagator. And this renormalized propagator here, I denote by, in that case, well, I denote by a double line. For example, for the singly occupied. So this is now with all self-energy insertion included. And that's what you call skeleton expansion. And then the self-energy diagrams, yeah, they have to be calculated with a full propagator in thing. This is the double line. And finally, there is the one for the singly occupied state in second order as function of z, which is given by now two diagrams, because this one is connected to the empty state first, and it's connected to, and now I need my wiggly line, it's connected to the doubly occupied state. And here it means you start out with a singly occupied state. A band electron is traveling with this empty state in that direction. So you see the arrows mean something here. They're important. This is a Fermi function. This is 1 minus Fermi function. And here it goes the opposite way. And these are the diagrams. And this, because these are all diagrams without any crossing of band electron lines, constitute NCA. That's the NCA. Okay. It's basically it. There's one thing in order to be able to really do calculations. You want, no, these are pseudo-propagators. They're not the real propagators. And that is not what you want to calculate. You want to calculate the Green's function. And the Green's function is a little bit a more complicated beast. Yeah, sure.
So these are actually a set of integral equations.
Yes, okay. Oh, thanks for pointing. Yeah, I should have mentioned that. Now I'm getting close to my limit, so I'm starting to become. Okay, thanks for interrupting and telling me that. Now, this is precisely the point. So you see here, this is the full propagator. So this is actually R sigma equals 1 over z minus E sigma minus sigma sigma. That is included here. So self-energy of the zero contains the self-energy of the singly occupied state. Likewise, the self-energy of the doubly occupied contains an integral equation, because that's what's standing here. Just insert a sigma here. Contains an integral equation involving the singly occupied self-energy. And the singly occupied self-energy contains, actually is related to two integrals which contain the empty and the doubly occupied self-energy. So that's a coupled of system of nonlinear integral equations. And one has to be aware that, showed you in the beginning, you have those wonderful, nice structures at the threshold. Those are algebraic divergences, in fact. So they go to the, like, 1 over e minus e threshold to the some power. Yeah? And you better take care of really following those divergences properly, and eventually also the exponential decay. I mean, you have this exponential tail out there. So this is not a trivial thing to solve, but you can do that. So the thing you do is you use a logarithmic mesh with an accumulation point around this threshold. You make an adaptive mesh, follow the threshold, and then you can really resolve that nicely. And that leads to the pictures I've shown you in the beginning. Now, let me take a few more minutes to show you how to calculate Green's functions. I mean, that's the actual thing we want to do, and then show you what the result of these type of calculations are. So you already used that none of us European professors sticks to our times. So I will keep up that tradition, but not as long as Antoine did. Hopefully. And that was pretty bad on Tuesday either, so. Anyway, so the Green's function. Yeah, the Green's function, you have now write the Green's function in terms of these operators. Let's call them x, m, m prime. It's defined as m, m prime. These go on the name Hubbard operators. These go on the name Hubbard operators. And the Green's function, the true physical Green's function for the d electrons, this looks, for the particular simple model, in case of multi-orbital systems with more complicated matrix elements, things look a little bit different, but the structure is more or less the same. So it's the Green's function consisting of x0 sigma combined with an x sigma 0. Now you may read this as an annihilation operator because it makes an occupied state into an empty state. But careful, those guys do not obey fermionic commutation rules. And there's a second part, namely, you can also start out from minus sigma and go into the 2 and go the opposite way. And that's just a way of writing a Green's function with two lengthy operators to put them into the indices as function of Laplace transform Z. Now, in some sense, if you look at that thing here, if you, now comes a little bit of a fishy argument, if you can, think this is some kind of some kind of density operator, because it contains a 0 here and a sigma here, so you can write the sum in the way of d sigma, d dagger sigma. Then you have a kind of two-particle Green's function sitting here. And two-particle Green's function, the lowest order, typically amount to some bubble diagrams. And in fact, what you can show is that, well, not easy to show, but it is to show, one can show, let's write it that way. The point is you can write down the expression, you have to somehow then insert the perturbation series in the expression, resum diagrams, and that's a roughly two and a half pages calculation. But one can show is that in the diagrammatic language, this object here, this should be sigma of Z, amounts to the following diagram. And now it becomes complicated to draw these doubly lines. We have a wiggly line here, and we have a double wiggly line here. So here we have frequency I omega n running. Actually, this is of I omega n. Here we have frequency I omega n running, and plus higher order diagrams, which we ignore. And there's a similar expression for this thing involving this one. You can actually imagine how it looks like. Yeah? It's a similar thing, just the wiggly line is replaced by the zigzag. Now there's one subtlety in evaluating this diagram, because it now contains a convolution of these objects, and the analytic expression of that guy is in fact 1 over partition function. That's the price we had to pay because we can't have linked clusters theorem that kills partition function. We need that object, so we have to calculate the partition function. Then there's an integral over our contour, dz over 2 pi I e to the minus beta z, and then comes the combination of R0 of z times R sigma of z plus I omega n, plus higher order. That's the expression you get for the Green's function, and a similar expression you can guess now how it looks like for that object here. And then you can again use the spectral representation, because as before, you know where the singularities of, or the poles, or the non-analyticities of those guys sit. This one has only one on the real axis. This one has only once shifted somewhere. It's like the bubble diagrams in standard perturbation theory. Just you can't use Poisson's summation formula, but you can relate this into two contours, one running down here, the second one running up here, and then you combine those two, the infinity goes away as usual, and you end up with a contour integral, which is, and that's the last formula I write down, then I show you a figure, which is simply, well, simply 1 over zd times the integral from minus infinity to infinity, the epsilon e to the minus beta epsilon, and then comes once the spectral function of the empty state multiplying R sigma of epsilon plus I omega n. Now this is well defined because I omega n is always positive, always non-zero, so you never hit the real axis. And the second part goes over the I omega n branch, which where this has singularities, this goes with a minus, and then you have the R0 evaluated at epsilon minus I omega n, because you have now shift everything down, and then the rho sigma of epsilon, and that you have to evaluate. Now, why do I write down these expressions? Well, the reason is very simple. Remember how the structure of these rows looked like. In fact, what you can do now is a simple analytic continuation, because you now just set I omega n to omega plus or minus I delta as you like. And you're on the real axis. So you don't have to do any analytic continuation. That's done for you by having an exact formula. Well, the point is, this one, remember, this one had a very small spike at the threshold energy. This one had a very small spike, or very large spike, at the threshold energy. The spikes were not at the same place, but they were different by TK. So that tells you this will give you a contribution which has a strong spike sitting somewhere slightly above the Fermi energy. Likewise this, and that's a condor resonance. And the second thing is, this had a broad peak sitting out at 0. This was concentrated around, well, roughly E sigma. And there's a second contribution, and that gives you the Hubbard band. And likewise this one. And the same holds for that one here. So you can, from the knowledge of this guy, you can already infer how the spectral function will eventually look like. And now we have to, so this is the end of my presentation regarding the analytic part. I want to show you two pictures, if I may. So if there are any questions regarding this stuff, ask them now or be silent forever.
So
yeah.
What is the small parameter in the
There is none. There is none. It's just, okay, there was a long time people were saying this is a 1 over n expansion. So in fact, what you can do if you have, say, this is an SU2 model. Okay, so you have just spin degeneracy. You can extend that to a model where you have n-fold degeneracy of your local level. And then it turns out that this diagram carries a sum over all these levels. So this carries an n. This one does not, sorry, this one does not, because here there is no degeneracy. So this diagram actually, if you now rescale your v squared times n, like in a DMFT, you rescale t squared times d is a constant. Here you make v squared times n a constant, and this goes down like 1 over n. And in the limit n to infinity, everything that goes beyond those two diagrams vanishes, like 1 over n squared or something. Now the big problem is nobody's really interested in the limit n to infinity, so one has to go to the finite dimension, finite n. So typically you do the calculation in n equals 2. So 2 is infinity in our sense. It works pretty well, has deficiencies. The thing becomes dangerous if you go beyond this type of NCA and try to include higher order diagrams. Because then this argument is misleading. And that's something what my colleague, Kurt Schönhammer, did parallel to me. One of his PhD students made an extension of that. That was my PhD actually extending this approximation. And they were guided by the 1 over n argument, and they screwed up particle hole symmetry by that. Because then one of these diagrams is unimportant, and especially in the particle hole symmetric limit, the approximation fails. So if you go pragmatic and say, fine, I take this as the approximation, and I just add all diagrams I need for the next order, then things are fine. So it's a dangerous argument. It doesn't take very far, actually. So there is no small parameter here. Yeah? This one? Oh, no. It was just how you call this, a kind of hand-waving argument. Now, the point is you have to really write down okay, this is now a Green's function. You have to write down the proper expression containing all the resolvents and operators, and then look how the perturbation series evolves. And it turns out that, in fact, this is the first diagram that appears. Now, seeing this, you could say, okay, fine, this reminds me of standard Feynman perturbation theory, where these typical two-particle propagators, they start with a bubble. And then you say, fine, this looks like a two-particle operator, and then you have here a bubble. But it's it's just hand-waving, so don't take this too deeply, just take it as a kind of motivation.
My question is, do one in this scheme, does one start always with this two-particle Green's function, or if I want to go to the basic one-particle Green's function?
This is the one-particle Green's
function. No, it's involving 4 fermionic operators, isn't it?
No, actually it's not. This is the replacement of the D operator, and that's the replacement of the D dagger operator, those two. So you have to rewrite, in order to do that, I mean, I did this in the beginning with the normal matrix elements. You have to rewrite your D operator. D sigma is the sum over M, and then M D sigma, right? So just insert a 1. And then you see there are only 2 combinations left, namely this is given by, if that operator is the 0, then this acts on the 0 and gives you a sigma. And the second combination is if this is, no, that's the only one, in fact. Right? And the D dagger, you can do a similar expansion. And then you simply rewrite the D here in terms of these operators, and that's why you end up with this. It's just everything has to be replaced by the eigenstates of the Hamiltonian.
Why is it called non-crossing?
Oh, because there are no crossings here. So these graphs do not contain any crossings. Yeah. This name has been coined by, who the hell was that actually? Piers Coleman, I think. I think it was Piers Coleman, some of those. Or Yoshi Koramoto. I think Koramoto was the first one to call it not a crossing. It just contains any crossing of Bendel. Nice. Call it second order self-consistent perturbation theory. NCA is shorter.
In calculating the double lines here.
Okay.
In calculating the double lines, also you left out the crossing diagrams, or?
Yes. So basically, you insert those expressions for the self-energy. I mean, you can write down the analytic expression and just insert these expressions into your equations. So what you do in practice is solve that iteratively. So you start off with a certain sigma, then do one step of integrals, get a new sigma, put this into the integrals, and iterate until converged. Takes 15, sometimes 10 iterations. It's pretty fast. Conversion is pretty good. in most cases. Okay, just, yeah. Yeah, yeah. Well, one has to be a little bit careful. What I've been showing you here works reasonably well for the Anderson model. In fact, in order to get, for example, condor temperature right, in order to get everything right, you have to be a bit more careful because this is not sufficient. So you have to take into account the first crossing diagrams. That's what I did in my PhD thesis. And then you can actually show analytically that Tk, not the prefactor, but the exponential comes out right. Here the exponential is wrong. It's exponential, but with the wrong exponential factor. And also the position of the Hubbard bands and the weight distribution is slightly wrong here, at least for moderate U. For large U, it doesn't matter, but for small U, it's slightly wrong. And if you want to do the condor model, you can do that because you can represent the spin operators. You can also represent by the Hubbard operators. And then you can actually use the whole thing. But it turns out that, unfortunately, these first order objects, they collapse to constants. So you have to take the next order. Yeah, the next order is the one that enters in the condor model. That's a subtlety. But for most cases, you're not interested in condor model anyway, so the Anderson model, that's sufficient.
So this prefactor change can be understood in some, there was a variational wave function that people wrote down for the condor singlet state.
Yeah, Varma-Jaffet.
Yeah, by looking at the particle hole excitations and all. So they will also have the crossing particle hole excitations, and that's why the prefactor comes out wrong. And
Varma-Jaffet is to some extent a simplified Gutzwiller, and the Gutzwiller is to a large extent NCA.
Oh,
Cum grano salis. Okay, now spectral function. That's something I should show you, in fact, because that's also relates to my presentation on Tuesday. What I show you here are two curves. This is the spectral function. You have seen this already several times now. What do we expect to have is Hubbard bands, condor resonance. And the blue curve is what I did just now. This is the NCA calculation, actually the improved version, but that doesn't really matter. And the red curve is NRG. Now you see two things here. First of all, the Hubbard bands out here, they are a little bit more developed. They're more compressed. And if you really look at the height is actually better than NRG. So that's what I told you. NRG typically has a tendency to redistribute spectral weight not quite correctly. The second thing is, and that's the actual killer for NCA. That's why you can't really use it on a large variety of systems, is that behavior here at the Fermi energy. You see the blue curves overshoots the red one. The red one has this wiggle I told you already about. Don't mind for that. But the red one stays below that dashed line. Now that dashed line is something a French physicist called Friedel showed in the, I think, 60s round, that this is the absolute upper limit for the spectral function to go. It can't go beyond that point, because otherwise you would violate unitarity or causality. And that means NCA violates causality, right? So it becomes too large. And this is a finite temperature calculation. It's not zero temperature. This is a rather not too low finite temperature. So it overshoots already at finite temperatures, and it overshoots significantly. And that means if you try now to calculate a self-energy from the NCA by inverting the Green's function, subtracting out the hybridization function, then you will end up with self-energies that have positive imaginary part for a rather big portion of the energy range. And that's the so-called NCA pathology, and that kills you. The problem is it kills you self-consistently in the DMFT, because there you generate your low energy scale self-consistently, and if that becomes larger than for example, the original model, and that happens from time to time, then you're dead earlier than you would be in the impurity model. Now, the nice thing is if you're in the insulating regime, you don't have any ASR, and then the NCA does fine everywhere. So there's no pathology. It's just the Fermi liquid it can't do. So it does well with the insulator, local moment, but it can't really do the Fermi liquid. And for implementations, I told you, you can actually also use that to calculate more complicated systems. Just to highlight from my earlier, yes? Yes, good. First one who realizes that, that also is, this is not a bug, because we had this was done for a box, yes, and the box, just because you have steps, you get these non-analycities. So that if you have smooth one, they're gone. Okay, and what you can, okay, and this is the final picture, sorry for extending. This is now a calculation, a DMFT calculation for a model that usually nobody can really treat in DMFT because it's a TJ model, and the TJ model is one where your Hilbert space for the band states is restricted to singly and empty state only, so you don't have the W-occupied state, which means you have to represent the Hamilton operator already in the Hubbard operators. Those two only, not those. You don't have any fermionic degrees of freedom. So action-based things like Monte Carlo or so, they don't work because you don't have an action formulation for the Hubbard operators. Well, you can try to do that, but it doesn't really work. And Monte Carlo for that doesn't work at all. So that's one of the few cases where I'm proud to say I'm the only one can do that. With NCA, you can try to do that with NRG, in fact. And the funny thing is NRG here has the problem of broadening, because what you see here are those very fine structures, right? Here, this is, this is the TJ model in the antiferromagnetic phase with a rather small doping, so 2% doping. DMFT for that. Antiferromagnetic solution. And what you find is a very, not a typical ISR, lower Hubbard band stuff. The upper Hubbard band is infinity anyway, but you find lots of these peaks. And if you now go back to something done by Strack and Vollhardt and analyze the behavior of one hole in the Néel background, you will realize this has a bound state, because if you have a Néel background, put one hole and move that hole, you generate a string of misaligned spins that gives you a linear potential for the hole, which is a bound state, and the bound states are those lines here. And you see it beautifully matches. So this DMFT with finite doping, well, describes this, this physics of a hole in an Néel background with a certain broadening. And if you try to do that with NRG, you will find out that you might be able to see that one. You might be able to get a glimpse of that one. The other ones are completely washed out due to the broadening. Okay, so that is what I wanted to show you. Sorry again for overdrawing 20 minutes. I hope it was worth it. So this is a technique you can really use for doing computations where you need, maybe not at the Fermi energy, but you need some kind of good resolution on the real axis directly without analytic conjugation and a quick shot for those models. Thanks. Oh, and as I said, there will be a script available where everything, including these figures, is on the